Thank you so much for having me. First today's talk, I'm going to talk about mostly number theory, but I will say that how you can use homogeneous dynamics to use to solve problems in Diophantine approximation. So I will start with a very basic Dirichlet's theorem, which is kind of the heart of Diophantine approximation. And I'll start with Rn. So if you take any vector x in Rn, and if you take any large number, let's say q, then you can always get non-zero integer solutions to these two inequalities. So this is q dot x, this is the usual dot product. The norms I'm using are in the supremum norms, but actually it doesn't matter. Okay, so this is kind of saying, this is quantifying the fact that rationals are dense in Rn. And immediately it follows, so that I call as Dirichlet corollary. That for any x in Rn, you can get infinity. So if you use, so there are two inequalities. So if you just plug the second inequality in the first one, then you can say that there are infinitely many non-zero integer vectors such that q dot x plus q naught is less than 1 by q to the power n. Okay, so let's see what we can say in case of QPN. So QP, first let's just define define QP. So you have Q, and you can have the p-adic norm, and then you complete it, and that's exactly the space QP. It's a totally disconnected space, and okay, so in the case of Rn, we had this chain of sets. So you have Z, then you have Q, and then you have R. Here also you can think, let's say Z1 over P, and then Q, and then QP. And Q is dense in QP. And moreover, actually, this Z1 over P is dense in QP. So you can also take Z. So the fact that Z is actually dense in the unit ball of QP makes the Diophantine approximation a little bit different, and it's very natural. So let me define let me write down the Dirichlet's theorem in case of QPN here. So almost the same statement, x in QPN. So I'll say ZPN actually. Then for all large Q, these two inequalities will have integer solution. Okay, so the difference is that here you have both Q and Q naught. So you have denominator and numerator. Whereas in this Rn case, it's only height of the, so height is determined only by the denominator. And the reason is very simple. It's because Z is dense in ZP. So if I don't have Q naught, then it's kind of obvious, because you can like fix one Q and then you can vary, you can take any Q naught and then it's always going to give you answer. So to say something interesting, we should have bound on both Q and Q naught. And why did I restrict X to ZP? It's because if I don't, then only thing that changes is this constant. So depending on which ball you are in, so if you are in a ball of radius P, then this constant would be probably P square or P. Okay, all right. So here also you can talk about Dirichlet corollary. I'm not going to write that. Now there are two ways to, so now that you know that by Dirichlet's theorem that this kind of stuff happens for all X, you want to know for which X you can improve these inequalities. And then since I talked about two kinds of approximation, so one is where you have two inequalities and one where you have just one inequality and one follows from another. So you can actually talk about improvement in both of these setups. So so if you want to improve Dirichlet's corollary, meaning you want to look for X such that you can say more than Dirichlet, what Dirichlet corollary says, then these kind of approximations. So let's say I replace, so replace 1 by Q to the power n by some psi function. So instead of 1 by t, you can take any psi function. And for this talk, I'm going to always restrict myself to psi to be decreasing. Actually, people also study when it's not decreasing, but then it would be more it's subtle, so I don't want to get into that. And these kind of approximations generally we refer as asymptotic. And then you can also try to improve Dirichlet's original theorem, so Dirichlet's theorem, and that we say as uniform. So there you want to study all those X such that you want to replace 1 by Q to the power n by some psi of Q, capital Q. And most of, so these type of things are well studied, but this one is not very much studied, but it's actually recently people are interested in this kind of approximations as well. Okay. So now how dynamics come into picture? So I'll just first talk about R. So let's say you want to approximate a point X in R. Then the idea is that you look at X inside SL to R mod SL to Z. As a UX, where UX is 1x01. And then, okay, so this is the number theory side. And this is dynamics. So the better you can approximate X, the idea is that the better you can approximate X, this orbit of UX, so what is GT? GT is a diagonal flow. So this will go to cusp in that manner. So however you want to approximate this, the same kind of behavior or the corresponding behavior will happen here. And this was due to Dani initially. So we generally refer it as Dani's correspondence. So let me just quickly talk about more general Chi function and make it more explicit. Okay, so what is W Chi? W Chi is where you change this 1 by Q here, Q to the power n by Chi of Q to the power n. So since I'm just restricting here myself to R, I'm just saying X in R is in this Chi approximable if, as you can expect, Q X plus Q naught should be less than Chi Q for infinitely many Q. And what does it really mean? It means that if I draw this rectangle, so let's say the length of the y-axis, this part, length of the y part is capital Q, and then the length of this is Q, 2Q, and this is Chi Q. So saying that this happens means that this point, this lattice, comes back to this rectangle again and again. So I want to write that down. So this is just X in R. There exists Q unbounded, so maybe Qi going to infinity, such that let me put this R. So lambda X intersected with R is non-empty. So lambda X with R, so R is actually Ri because R depends on capital Q. So this is what it means by Chi approximable numbers. Okay. Please feel free to interrupt me if you have any question.
So R is not fixed. R depends on.
Yeah, so R depends on capital Q. So that's why here there is I. Yeah. Okay, so now let's say so this was in R. Now what do we do in case of QP? So you cannot just take SL to QP because there is no lattice. But you can think of QP inside SL to QP cross R mod SL to Z 1 over P. So you will have matrices with two coordinates. So let's say I have X here, then I want to look at that point inside the space as UX, where the P part is exactly same as previous case, and the Archimedean part will just take identity. And then the diagonal action going to define GT as this P to the power T. So the p-adic part, so this is the P part. And this is the R part. Here I'll take this. And then so these are UX and GT. And then the idea is that, okay, can you do the same thing as here? Okay, so you can see that there is probably you can start with x and say that okay, x is very well approximable, and then you can get same kind of argument. But if you have to come back, like if you have that this orbit goes to cusp at a certain rate infinitely many times, if you have to come back and say something about x, then you may have some trouble, because here you have the lattice to be z1/p, whereas you are actually just approximating by z.
But when you multiply by pt, you contract or expand.
You contract.
The basic part you usually contract.
Yes, so you contract because it's p to the power t, where t is like t is an integer.
X gets contracted.
Yes.
And then the real part gets expanded.
Yeah, so let me write down the points in the lattice. So I can do it here. Okay, so what are the typical points in GT UX? Said 1/p2. So let's say Q not Q. Then this is going to p to the power minus t, since p to the power t. But if you take norm, it's going to be p to the power minus t. Q naught plus Q x, and then you have Q, and then the other part is p to the power minus t by 2Q. So now if you take, so in this case also, when we are saying that it goes to the cusp again and again, then I mean that, so in case of
it looks like you have contraction in both components. You want to preserve the volume, probably due to minus basic part. Because p to the power of t will contract also.
Yes, okay, so let me write.
Everything will be contracted.
No, so if I, okay, so if I write the shortest vector in this space, so that is going to be C is the product of the p-adic norm and the infinity norm. So C of any typical point, so delta of this is going to be a maximum of p to the power minus t, Q naught plus Q x p, and then the p part of Q times p to the power minus t by 2, the infinity norm of 2Q naught. So this is the shortest vector, whereas in this case it was much simpler in the R case. So maybe you may expect that if you have something here, maybe you don't have exactly Diophantine approximation in the usual manner in case of QP. Because you're having, like, for instance, you have this Q with p-adic part, then you also have like product of two things. Okay.
Sorry, so just to clarify, so here you have a p-adic part and an Arbor.
Right.
And the reason why you have an Arbor is because of there you need control over Q0. Is that the reason, or?
The reason why I have R here, because if I don't, in this case,
right,
you're saying, so here it's p to the power minus, also you were right, so it should be minus
Yeah,
t.
that's what I meant.
Oh, okay, yeah,
Okay, no.
right. Yes. Yeah, so if you take the determinant, then this one is p to the power t, and then like norm of that is p to the power t, and this is cancelling out.
So I think Florian is right. You need to control Q0, and there is no way to do it. Just
so that's
yeah, right.
add
No,
an additional. Okay.
Yes.
Yeah, that's, okay.
Yes.
Okay.
Right. Okay. All right. So I'm just going to say one more thing about QP and then I'll go back to our case. So this is like a work with Ghosh and myself, and it's from my PhD. So, I mean, I'm just going to talk a very brief part about it, which is that instead of defining the objects coming from Diophantine approximation, maybe you want to define the approximable vectors depending on the dynamics. And it's not clear that whether you will always land to the same thing. So in particular this case, so omega hat eta, and this is just for QP, you can define y such that qy plus q naught p naught is less than 1 by so you will see that this is exactly to fit the dynamics definition. So let's say I have this definition that I call something to be eta approximable if this happens for unbounded unbounded many this, where this q tilde is not in Z, but it is in Z1 over P. So let's say I define such a weird set, and so we show that this is exactly this has exact correspondence with the dynamics, and probably you can see why I have this Q with P naught, because I also have the same in the dynamics part. But then I have to somehow probably get some information about the usual Diophantine approximation sets that people are interested in. So actually, omega hat eta is not exactly the usual, but you can say that omega hat of eta is inside omega of eta minus epsilon, where what is omega of eta minus epsilon? It's exactly, so I did not write, so like here you would have q dot x plus q naught so if I just add a eta here, so those are the sets omega eta that come from Diophantine approximation. So I'm just showing that actually it doesn't matter when you are working with exponents. It would matter if you have some other random function, and if you want to connect dynamics, then you may have problem. But since this happens, so this happens for all epsilon greater than 0. So actually, when you are looking at exponent, then it doesn't matter. Okay, so let's come back to real case. And I won't talk about QP for some time now. Okay, so as I said, we are interested in this W variable approximable sets, which are just all those such that you can improve the Dirichlet exponent by epsilon. So what is the size? So first question is, what is the size of this set? So it's not very hard to show that. So this is just like all x such that qx plus q naught is less than 1 by 2 plus epsilon, 1 plus epsilon for infinitely many. So this is a lim subset. You can write it as all q greater than k and then union over k of this. These are just balls. So Q naught and then balls of Q naught by Q with radius. Okay, so in order to show that this set has measure 0, it's enough to just show that for every epsilon, this set has measure 0. And this set is exactly lim sup. So how do you show that a lim sup set has measure 0? You use Borel-Cantley. And you can see it would work out because here the lengths are 1 by q to the power 2 plus epsilon. But you have q naught. But q naught can be more than q because you are looking at, so I'm looking at x in 0, 1. So q naught can be f max q. So therefore there one q cancels out. So you would have summation 1 over q to the power 1 plus epsilon, which is less than 100. So this set has measure 0. So lambda is a Lebesgue measure. So even in higher dimensions, the same proof works. Okay. The next question, what can you say about manifolds? So let me be more specific. So let's say you take a line in R2, and let's say this is just y equal to x line. Then you can show that any point here is variable approximable, because the definition of variable approximable is that q dot, so now you would have xy, so x1 q to x2 plus q naught is less than so this is the definition. So this should happen for infinitely many, but if you have coordinates to be dependent on each other in a rational way, then you can always say that this will become 0. Okay, so that means it's not true that if you look at the same set inside a curve, then it also has measure 0, right? So that is not true. So then the question is, what is the right condition on the manifold such that you can say that the same thing as in case of Rn holds, right? Okay, so this was so first Malher, this was in 1932. So he conjectured that if you take, instead of line, if you take a parabola, and let's say you are looking at, so let's say this is C, and you are looking at C intersected with variable approximable, then the measure of this should be 0.
I think for parabola, he actually proved it.
I think
All right. But for higher powers.
Oh, okay, yeah. So he proved for parabola, and then he conjectured for these kind of curves inside Rn. So this is Malher's conjecture. That the same thing should hold. So lambda 1 of this C intersected with variable should be 0. And this was a theorem by Sprindzuk in 1960s. And in 1980s, he conjectured this. So maybe I can erase this part. Okay, so the this is Sprindzuk's conjecture. So let's say you have a function f from an open subset of Rd to Rn. You assume that n is less than n. And let's say you have the assumption that f is never planar, meaning f of b cannot be inside any affine subspace of Rn, and this holds for all b. So if you look at any local part of your manifold, it should not be flat. Then f inverse, then the same conclusion as before should be true. So f inverse of the variable approximable intersected with u must be 0. Okay, and this was proved by, so this is now a theorem by Kleinbock and Margulis. In 1998. And
by the way, wrote down when I was a postdoc here.
oh, okay.
Yes.
Nice.
Come back.
Okay, so let me just say that then how do you think that this can be proved? So definitely you have to use some sort of Borel-Cantor. So in order to do that, you have to know the estimates of those sets. So first they like connected using Bani correspondence. They connected this problem in terms of homogeneous dynamics. So let me right here. Okay, so variable approximable in terms of dynamics would mean that all those x such that there exists some delta or epsilon greater than 0, such that if you look at this or this GTUX orbit, then it should go to, there is a subsequence which should go to the cusp at a certain rate. In this case, it's just e to the power minus delta tk for infinitely many tk. So this is again, I mean, it's a lim subset. So what do you want to estimate? So this is lim sup of ET, where ET is all those x such that, so here it should be x. So this is variable approximable. Now we want to do it with the inverse of f of the variable approximable. So I want to say all those x inside the open ball such that here it should be f of x. And that changes the whole problem. Like it's, if I don't have f of x here, just x, then it's not so difficult as we have seen.
So what is delta here?
Okay, so delta is the small the length of the smallest vector of the lattice.
And the epsilon, does it?
So here I suppose this should be epsilon.
Okay, thank you.
Okay, so what do we really need to do in order to apply Borel-Cantor? We need to have estimates of this kind of sets ET. So x in a ball of Q such that delta of GTU fx. So I want So maybe we want to estimate these kind of sets and then use Boyle-Cantley. And the proof was done. The main part of the proof was to estimate these kind of sets. So maybe I can just write down the proposition and I will come back to that if I have time. So this is the proposition. So for all x in U, you can find a neighborhood of x such that for all epsilon and t, maybe epsilon should be less than 1, lambda x in B such that so the time that it spends at the orbit which spends a lot of time at the cusp should have small measure. So this should be less than equal to C epsilon to the power alpha and then size of B. Now this alpha and C, that would depend on the function f. I think alpha will also depend on the dimension of the manifold. So this will depend on f and d. So if you have this proposition, then you can just use Boyle-Cantley. Okay. So then I want to talk about more results in this direction. So instead of variable approximable, you can just, instead of 1 by t to the power 1 plus epsilon, you can replace by any function psi. And then you can ask the same question as Sprindzuk conjecture, but replacing this variable approximable by, so replacing this by W psi. And then you need to have some relation on psi to determine when it is 0 and when it is not 0. Okay, so this was, I think there are two papers. One is by Barney, Kleinbock, Margulis, and where they prove the convergence part, meaning, so if you have the summation of psi converges, then they show that the measure should have 0. And then in another paper with Beresevich, they prove the divergence part. So this kind of results are called as Khinchin-type theorem. Okay, now you can ask more. So instead of, so here you see that this is nothing but asking that what happens if I take f star lambda, then what is the set of variable approximable? So these questions are terms of f star lambda. Now instead of f star lambda, you can ask what happens if you have a fractal measure. So this was a work by Kleinbock. I'm writing just K. Kleinbock, Linus-Strauss, and Bark-Weiss. Okay, so mu, I'm going to just talk about dimension 1. Because in higher dimension, I have to then define many other things. So I just let's just say that mu is a fractal measure. So it is supported on some fractal, which satisfies open set condition. Like I don't need that for dimension 1. Then mu of f star of mu of this variable approximable, and f is same as this assumption, so I'm not going to write it again and again. So f is going to be same for all of these theorems. Okay, so they show that this has to be 0.
Okay, some assumptions on mu.
So mu is for, so this is for dimension 1. Mu is just a fractal measure. Fractal.
What does it mean?
Okay, so mu is supported on a fractal set. That's what I mean.
We can have a measure supported on VWA.
Okay, so
there are some assumptions. I mean, I have to assume some decaying conditions.
So I don't want. Okay.
It's just not true.
So mu is a fractal measure, but with also some decaying condition. But I don't want to define decay, what decaying means. Yeah, it means that, okay, so roughly speaking, it means that if you take just affine functions, then it should be good with respect to, when I say good, it means that it should have, like if I look at the function, so it should behave like a polynomial map, but with respect to this measure. Okay, all right.
So can I just take the uniform, the Hausdorff measure on the Cantor-Smith set, for instance? Would that be legal?
Yeah, that's very
yes, yeah.
good. Very good.
Okay, all right. Now I want to talk about, so these are all about reals now. I don't want to write it again, but I want to mention that this work in case of QP was done by Kleinbock and Margulis. And these works, Khinchin-type theorems, in case of QP and more generally was done by Shreyasi Datta. So maybe I should write that because that's what I'm going to talk next. Okay, so Mohammadi Golsapidi, they prove, so okay, so now the setup is more general. So instead of QP, you can just take QS, where QS, S has finite, S is a space of finitely, S is a set of finitely many valuations of Q. So QS is going to be just like QP1, and you may or may not have R. So there are two, like you may have only purely algebraic effects, or you may have reals as well. Okay, so they proved BKM style results. So the S-arithmetic version of BKM, so meaning Khinchin-type theorem. And then they also proved, just for QP, they proved the divergence result. So this is divergence, and this is gone. Now I can state theorem A. This is by this is with my supervisor. Okay, so far I was just talking about approximations where I did not have, so it was just q dot x, and then you were looking at the distance from its nearest integer. But then you can also have a theta, and that is what called as inhomogeneous. So first let me write down the theorem and then I can say what it is. So let's say theta is in QSN. Then you can define it depends on whether you have infinity or you don't. So let's say infinity is not there, then you would have this to be less than chi a tilde, where a tilde is same as before, a naught, both a and a naught. And if infinity is there, then you can just have a. So these are, so if you have, so let's call this as W, I don't know, W theta. So if this happens for infinitely many a, so if I in particular take theta to be 0, then that's the homogeneous, all the homogeneous results. So the theorem is W, I should have a psi here. Sorry, I'm writing. So F inverse of this . So this is the convergence part. There is no restriction on theta. And then also we have a divergence result. But our divergence result is for all S when infinity is not in S. And if infinity is in S, then we have a weaker divergence result. So even when theta equal to 0, the multiplace position was not done. Okay, all right. So that is theorem A, and then I want to talk about theorem B. This is a recent work. And this is with Shreyasi and Anish. So it's exactly the p-adic analog of Kleinbock and Margulis twice. So I'll not write down again. And in particular, it answers a question by Kleinbock. Okay. So I have 10 minutes, so I can probably just talk a little bit about the proof. So for that, I need to
just clarify. So you have this theorem A about this arithmetic case, but for the real case, it was known.
That's right. So it was right. So I should say that. So when
for theta, for those thetas.
Right. So when S is so this is by Baziai, Shreyasi and Bellani.
Both parts.
Yes. Yeah.
Without this weaker condition.
Right.
With optimal condition.
Yes, with the optimal condition. Okay, any other questions?
What's the function of f? Function f?
So same assumption. So f is analytic in this S-arithmetic course. So and it has the same assumption as before, that it is not non-plan. It is not planar, sorry. Okay, so in order, so I want to talk about this theorem because this is more recent. So I need to talk a little bit about the quantitative non-divergence. Yes.
Can I first ask another question? So this result of Kleinbock only holds for variable approximal, but not for the W.
Right. Yes. Very good question. So it is actually still open. If you even for Cantor set measures, I think it's not known.
Okay, and so the same. So this is maybe so theorem B does not imply theorem A because of this.
Yeah. No. Yes. Okay. So maybe I can use this for. Okay, so I want to talk about the proof, but for like just to even say that like what is the main difficulty, or I have to talk about quantitative non-divergence, which was the idea by Kleinbock and Margulis to solve Sprindzuk conjecture. Okay, so first, before talking about quantitative non-divergence, so I should say what do I mean by non-divergence? So if you take ux, one parameter unipotent subgroup of SL and R. It was a theorem by Margulis in 1970s. That this neighbor diverges. So for any C lambda in this space, so SL and Z, ux of lambda should not diverge. And this is, I can restate this this statement. This is saying that if you take x in R such that ux delta is inside the compact set, so I should say delta of this is greater than or equal to epsilon. So the compact sets are where delta is greater than some number. So this should be unbounded. Okay, so now if you want to, so I want to just talk about first in case of dimension 2. So SL to R mod SL to Z. Now in SL in R2, if you look at unimodular lattices, then you can guarantee that there exists one number such that you cannot have vectors in the lattice which are both less than that specific number. So there should be an epsilon naught such that in this box you cannot have two vectors of a lattice, of not any lattice but unimodular lattices, because then that will, if you have, then it will not preserve, like it won't be that the length of the volume of the fundamental domain is 1. So that, let's say that is the epsilon naught. Now, if you look at this ux, where x is, let's say, inside an interval, then there are two possibilities. So one is that there exists one vector non-zero vector in the lattice such that no matter which x you take, ux of the vector is less than epsilon naught for all x. So this means that nothing interesting is happening, because for all x, only one vector is responsible for it to be smaller. And then there is another maybe more interesting part is that maybe for all v non-zero, you have that there exists some point where it goes beyond the epsilon naught. So supremum of ux v is then, and rho is let's say less than epsilon naught, which is fixed. So these are the two possibilities that can happen. And in both of them, the conclusion is that if you look at u of x lambda to be let's say delta of this less than epsilon, then that should be and you can so if this happens, then it's just an interval of length epsilon, so it has to be this. And if this happens, then you can write the left hand side as a union of balls. So the shortest vector that comes, that is always primitive, meaning it can be extended to a basis of SL to R, right? So whenever this happens, that means there exists a V such that ux v is less than epsilon. Now that means what is ux? Ux is just 1x01, and you're multiplying by v. We're really looking at an interval. So basically this left hand side is union of some disjoint intervals, and for different primitive vectors you will have disjoint intervals. You cannot have the same interval, and that's again because of this restriction that you cannot have two small vectors. And then you can just take rho slightly bigger than epsilon, and they are also disjoint. Then idea is very simple, that this set you can write as union of this disjoint sets, but they are inside the bigger disjoint sets, and you can, so this is of length epsilon, and this is of length, the outer one is of length rho, and you know that their ratios are just epsilon by rho. Okay, so the idea, I want to just write down these two things. So why this proof works is because x going to ux v for any primitive v, these are maps. So these are basically just polynomial map in this case, and these are the maps where you can actually estimate the sets. Like you can say that the size of this should be epsilon to the power something, right? So that should happen. That is one of the properties that we are using of this ux. And the second is just, this, which if doesn't happen, then more obvious thing happens. So supremum of ux p. Okay, so now if you want to do the high dimension part, then this doesn't anymore. This is not true. You can have two small vectors. So the idea is that if you have two small vectors, you form the subgroup that is generated by those two vectors. And then instead of saying that you cannot have, if you have a small subgroup, then you cannot have any further smaller vector. So replacing like small short vectors by short subgroups. Okay, so I should write down the statement of quantitative non-divergence. Okay, so let's say B is an interval in R and C and alpha are positive numbers. And let's say, and another thing is that here we are not really using the fact that UX is this. So we are using these two properties. So maybe we can change UX by any age. So age is a map from B to R. This Q and D is from Kleinbock and Margulis, 98. So A should be exactly same as this one here, that this function x going to 8x delta. Now delta was, in this case, it was primitive vectors, which are the short vectors. You can also talk about primitive subgroups. So this should be good. Meaning this, like you can compare the sets, and then second condition is almost same as that second condition. So if H satisfies these two properties, then the conclusion is that you can estimate. Is it gone? You can estimate the sets X and B. This is exactly what we wanted to do for Sprindzuk-type theorem, Sprindzuk's conjecture. So Hx of Cn. So delta of this is less than epsilon. Okay, so now, so this was a quantitative non-divergence. Now, I said here that Kleinbock, Lindesters, and Weiss were proving it for fractal measures. So actually, they proved the quantitative non-divergence version, but here, change this good. I was talking about with respect to the Lebesgue measure, but with respect to mu. And then here also the conclusion for mu. And mu should be decay, mu should be just a Federer. Mu should be just a doubling measure. Okay, now, so in order to prove this kind of theorem, you need to show basically that these two hold. And so you need to show that if you so maybe I'll just take 5 more minutes. Is that fine? Okay.
Yeah, maybe if you can make it quick. Yeah.
Okay. All right. So basically, what I wanted to say that in order to prove the same thing for QP, you need to show that these kind of functions are good. And in order to do that, you have to, like, they use mean value theorem. But in QP, there is no mean value theorem. So that is a huge problem. So I just want to quickly draw a picture. So in case of QP, you can define f double prime Ci function as in case of R, but there is a stronger definition, which is that you, let's say take B a ball in QP, you define f phi1 of f on B cross B minus the diagonal. And the definition is that phi1 of f xy is f of x and then you say that the function is C1 if you can extend it to this line, blue line. So even if you have that stronger definition, still you don't have mean value theorem. But maybe one can just, like this one looks almost like mean value theorem. But the problem is that now here, this is a function with two coordinates. So the main challenge of this work was to be, so they, in the Kleinbock-Lindenstrass one, they use mean value theorem left and right. So the main problem was to like get rid of mean value theorem. So find the right conditions such that this happens and then show that that condition actually is true for all the functions that we are taking. Yeah, I can stop here.
Thank you.